Okay, so let's see here. Here's where we left off last time. We talked a lot about path independence. We talked about the fundamental theorem of line integrals, closely related ideas, of course, because they apply to the same vector fields, right? The fundamental theorem of line integrals only applies to gradients. Path independence is an alternative property of gradients. Right, so they're very closely connected, and of course you can use one to prove the other, so that's nice. If you're going to use the fundamental theorem of line integrals, it only applies to gradients, but in particular you need to be able to find the anti-gradient. You need to be able to find this function f, whose gradient is your original function. And so here's the strategy we're going to use for that. If the vector field you're looking at, if that actually is a gradient, notice that that means that one coordinate at a time these match up as well. So that means that the first coordinate of our vector field has to be the x partial of f. Or said differently, f has to be the x antipartial of p. Right, and then likewise, q is the y partial of f. That means f is the y antipartial of q. Etc., etc. Okay, so altogether what that gives us is, I'm going to say these three equations right here, but of course those aren't the whole equation. What's the deal with all of this stuff over here? What's going on with these, C1, C2, C3? And these are what we call partial constants. Why a partial constant? Well, remember, the big idea for f is that its x partial has to be p. And okay, this would do that, but if you're going to be taking the x partial of it, I mean, anything whose x partial is 0, you could throw in for free. That would work just as well, right? So now y'all are accustomed to, in Calc 1 classes, when you're finding antiderivatives, to, you always say plus c. Right? And why plus c? Well, because constants are the things whose derivatives are 0. Here, we're not requiring that a single variable derivative be 0. We're requiring that a partial derivative be 0. And the thing about it is, any function that doesn't have any x's in its formula, its x partial is going to be 0. Right? So any function of only y and z is going to have x partial 0. So you can add not just a constant, but you can add any function of the other two variables, and then of course likewise for these other equations down here. So all together then what we really have is that the function f that we're looking for, the anti-gradient that we're looking for, keep in mind, anti-gradient, right, this thing, it needs to equal to all three of these things. But, of course, we don't know what these partial constant functions are. They could be anything. So, to say it a little differently, f has to be some version of this first equation, some version of the second equation, etc., and I get to pick what I want these partial constant functions to be. Anything that will make it possible for all three of these things to equal to the same function. So let's see this in action. A lot easier to see this in action. So here's a vector field, and again with the idea that I want to find an anti-gradient for this vector field, we're following the formulas on the previous page. This first coordinate, I'm going to take the x antipartial of that. The second coordinate, I'm going to take the y antipartial of that. The third coordinate will take the z antipartial of that. That's just copying from the previous page. Those are, of course, easy antipartials to do. It's polynomials, nothing to it. Now, again, if you're sloppy on this business about partial constants, you'd look at this and think, well, these functions are different, so not possible, right? This is what the x antipartial of p is, and it's not the same as this thing, and we lose, right? But we don't lose because, again, you have this flexibility. The x antipartial is, this, but plus any possible function of y and z. So what I like to think of this as, at this point, is a kind of a game. It's a little game that you're going to try to win. You're going to look at these three things. I need all three of these things to equal to the same thing. can I choose functions C1, C2, and C3 that will make all three of these exactly the same thing? And thus begins the game. Right? Now, how you play this game is up to you. My own little personal, I like to look at the x squared y and the x squared y, and I figure, okay, you know what? I feel like I need an x squared y in the third line as well, and I don't see it here. And that's discouraging at first, but then you realize, oh, yeah, but you know what? This partial constant over here could be any function of x and y that I want. And you know what? I think I want it to be x squared y. Right? So, boom. So we have x squared y in our expression. Likewise, xz there, and you know what? This could be xz right here. So, cool. We have xz in all three lines. And then lastly, let's see here, minus yz squared. And this right here could totally be minus yz squared. Like so. And so now, as required, this thing here that I'm calling f is equal to all three of these things, and we win the game, and we have ourselves an antigradient. Everybody see how that game works? So, okay, all right, now here is a silly observation. If you're going to find an antigradient, there had better be an antigradient. And we kind of knew that an antigradient was going to exist here because, look, you can take the curl. That's just a little bit of algebra. There's nothing to it. You take the curl, you do get 0. We have a theorem from last time. We know there's an antigradient. What we did here is find the thing that we knew existed in the first place. So what if it doesn't, though? And so this is an example to address that. If I were to suppose I'm interested in finding an antigradient of this vector field, and I take Green's operator, per our theorem from last time, I get that it's not 0, so I know there shouldn't be any antigradient. And this brings up a concern. If there is no antigradient, what if my game process finds one? Well, wouldn't that be bad? Well, of course it would be bad. You can't find stuff that doesn't exist. And if you think you found something that doesn't exist, then your process is flawed, right? So how does this play out? And I hope that the process fails, because there is no antigradient to find, right? So play this game. Right? And again, you follow the usual process. You take the x antipartial of the first coordinate and the y antipartial of the second coordinate, and you remember to add in your partial constant functions over here. And can I choose those constants to make these equal? And thankfully, no, you can't. You just try. I mean, entertain yourself until you're no longer entertained by the attempts, right? But there's just no way you're going to put a function of y, only y, right here, and a function of only x right here, and make these two things equal to each other. It's just not possible. So good news that failed, as it should have. Okay, so that's the story on how to find antipartials, and that finishes up Chapter 6 for us. And off we go now to Chapter 7. We have some groundwork that has to get laid before we can get into the new theorems. Eventually, just for foreshadowing purposes, I'll note that we are going to find kind of three-dimensional versions of all of the theorems that we just got through talking about in 2 dimensions. But it is 3-dimensional instead of 2-dimensional. Everything's geometrically quite different in some important ways, so we can't just kind of recopy them, right? I mean, this is going to be there's going to be some work to go into that, and one of the first things we need to do is talk about what a parametric surface is. Now, plausibility argument. Why parametric surfaces? Well, think about how prominently parametric curves figured in the 2D stuff that we were doing, right? Talking about line integrals. How do we compute line integrals? By pulling back through a parameterization, right? So we really needed to be able to parameterize curves to talk about vector line integrals. Well, we're going to need to be able to talk about parametric surfaces, whatever that means. So it would seem reasonable anyway to suspect, to be able to talk about surface integrals. All right, so here we go. So what is a parametric surface? Its position as a function of two parameters. It's very, very conceptually similar to a parametric curve. Parametric curve gives you position as a function of one parameter, typically time, right? And that causes you to trace out a curve. Parametric surface is just the same idea, position as a function of now just two parameters. So here's an example we've actually already seen. This goes all the way back to Chapter 1, Section 1.5. So you might want to flip back in your notes, flip back in the book, and find the example that we did. That was I think it was a homework exercise also, right? But anyway, we've written stuff like this down in some context, and the idea is that if you want to talk about points in this plane, here's a point in this plane, and if what you're given is a single fixed point on the plane and a couple of direction vectors parallel to the plane, I appeal to your geometric intuition. If you know one point on the plane and if you know two directions parallel to the plane, that does define which plane you're talking about, right? And how would I construct other points on the plane? Well, I'm going to say kind of do what you have to do. And you start off at your starting point, x naught. You go however far you need to in the v1 direction, and then you go however far you need to in the v2 direction. I mean, how far do you need to go in the v1 direction? Well, it's not going to be just 1 times v1, probably. I mean, maybe, right? But probably not. S, as a parameter, then, allows you to go as far as you want in the v1 direction, as far as you need to in the v1 direction. And likewise, T allows you to go as far as you need to go in the v2 direction. And now, geometric appeal, if you can, from this point, if you can go arbitrarily far in that direction and arbitrarily far in that direction, you can get to anywhere in the plane, right, by just tailoring these S and T appropriately. Okay. So that's the big idea, and notice what that means is I have position on my plane as a function of two parameters. Let's see here, color choices. Two parameters, S and T. And so I have X as a function of S and T. How we doing? Is that all right? Kind of analogous to the idea of a parametric curve. Two parameters gives me two directions I can go, therefore gives me a two-dimensional thing, in this case a surface. Okay. All right. Now, one downer about this, because there's two parameters, you do kind of have to let go of one of our favorite crutches on parametric curves. Remember, I push really heavily this idea that when you're talking about a parametric curve, let's call the parameter t, let's think of it as time, and that allows us to make this interpretation that the parameterization is tracing out the curve. Right? It's a wonderful little sort of physical metaphor for what's going on. Now that I have two parameters, I can't really have two different kinds of time. Again, that's just that'd be a really confusing sci-fi movie. I don't think that's going to be a helpful point of view. So you have to abandon this time point of view. But other than that, it's just like parametric curves. Okay, so we're going to be doing a lot of parametrizing of surfaces. It's going to be important to be good at that. I'm going to show you my favorite techniques for parametrizing surfaces. There are a bunch of examples in the book of parametric surfaces, but the book's examples are all what I'm going to call backwards. The book's examples, every one that I saw in this whole section of the book, was given a parameterization, interpreting what surface they're talking about. In practice, typically what you need is the opposite of that. Typically, you have some surface that just comes to you, like, hey, I need to do something with a sphere. I need to do something with some other surface, a paraboloid. How do you create the parameterization? That's what you actually need in practice, day in and day out in the real world, right? That's what you need. And oddly, the book doesn't have any examples that I saw, certainly not in this section. So let me show you my favorite ways to create parameterizations. My favorite, it's called the graph parameterization. You may recall that term. We had a graph parameterization for curves. Now, I'm going to strongly encourage that everybody look back and remind yourself of how the graph parameterization of curves works. I'm sure you'll remember quickly once you see it, if you don't already remember already. This is morally the same idea. The idea is that if you have, in fact, a graph, as we have here, z is a function of x and y. That's what it means to be a graph, right? Here's the trick. Whatever your input variables are, let those input variables be your parameters. It's just like parameterizing a curve. It's just that when you're parameterizing a curve, the graph was a curve in 2 dimensions. There was only one input variable. That became our one parameter. Here we have a surface that's a function of 2 variables. So we have 2 input variables to be 2 parameters. So it works perfectly, and for example, you'll notice very quickly that this equation right here is a graph, right? Z equals, right? I'm going to follow the rule. I see that x and y are my input variables, right? There, the x and the y are the input variables. I'm going to let x and y be s and t, following the instruction, right? Following the basic rule of graph parameterization right there. Just do that, and I claim we're done. It's all over but the shouting at this point. I don't have any more decisions to make or choices that I can make. So what's the deal with z? Well, here's the thing. If x and y are s and t, then that forces z to be that. And I'm done. I have my full parameterization. Position, x, y, z, functions of just the 2 variables, s and t. This is a parameterization for that paraboloid. Everybody see how that works? It's a real plug and chug, very convenient in that sense. A couple other examples just to show variations. There's no law that says your 2 input variables have to be x and y. Here, by contrast, I have y as a function of x and z. And that's cool, that's fine. Alphabetical order doesn't matter. Right? Whatever your input variables are, let those be your parameters. Like so. Right? Okay, so starting this example from the beginning, we want to parameterize this surface right here. It's not written as a graph. What are you going to do with that if it's not written as a graph? Well, write it as a graph in any way you can, and you're always going to be tempted just by reflex, I'm sure, as I am, to first look for z and see if you can solve for z, but of course that's hopeless, right? You've got a z in a polynomial term and you have z in an exponential argument, that's not going. You're not going to be able to solve for z. And you're not going to be able to solve for x for the same reason. But it's perfectly easy to solve for y. And once you've solved for y, you notice that the equation you have is exactly that form, namely y is a function of x and z. And as previously discussed, we let x and z be our parameters. And if that's what x and z are, then there's no way around it. Y has to be that. How are we doing on that? Does everybody see how this fits into that? How we result with this parameterization? Position is a function of S and T. And what's kind of beautiful about this is that I really don't know what this surface looks like. Right off the top of my head, it's pretty weird. I don't know what the picture is, but I can parameterize it even without knowing what it looks like. So, neat trick. Alrighty. One last example. This is what I'm going to call a spherical graph. Instead of solving for a rectangular variable, x, y, or z, as functions of the other two rectangular variables, here we're solving for a spherical variable, rho, as a function of the other two spherical variables, phi and theta. And to your concerns, possible concerns that, hey, I don't see the theta in there, cool, it's an easy function of theta then, right? The theta dependence doesn't have to be non-trivial. Perfectly fine to call this a function of phi and theta. Okay. All right, so when that's the case, basically the same idea works. The only little trick logistically is just write down the conversion formulas first. Keep in mind, of course, you do need x, y, and z to call it a parameterization, but what you're going to be plugging in for is in spherical coordinates, and so you want to convert to spherical first. And with that said, now it's just a matter of kind of plug and chug. I have here a formula for rho, and so all of these rows right here just become cosine phi. And as required, we have position as a function of two parameters. Again, our independent variables, phi and theta, the input variables, phi and theta, are our parameters. So, again, victory. Everybody all right? Okay. All righty. This next example is a little wacky and is, I'm going to confess, a little on the obscure side in terms of how often you're going to see this. And so it's pretty optional, and we're behind schedule. And so we're going to skip this example. You don't have to look at that. If you want to look at it, I encourage you to look at it. It's not a bad example. It's a cool idea. And this is kind of the surface analog of the examples that we did back in Chapter 1 where we were, you remember the ones with the bicycle wheel and the reflector, and it makes that little wacky curve. This is, vector algebra can be a tool with surfaces as well. So yeah, feel free to take a look. It's a good tool to have in your toolbox, but it's not required, and so we're just gonna skip this one this year. Okay, moving along. This next one is not wacky. This next one is very common to come up. This is my take on it. Sometimes the best way to parameterize a surface is to create a new coordinate system. I know that sounds like a lot. It sounds like a big ask, right? But it's surprisingly reasonable in a lot of cases. So here we go. For example, here's a surface called a torus, basically the surface of a donut, right? And suppose I wanted to parameterize that surface. It's a surface. We should be able to parameterize it. It's not a graph in any sense. In any coordinate system that we have any previous familiarity with, right, we are out of luck. We cannot use the graph parameterization of any version for this example. So what I can do, though, notice, is I can create a new coordinate system, what I'm going to call a coordinate system. It doesn't have to be a coordinate system for all of space. Don't think too big, right? I just need to talk about coordinates on the surface. And so in particular, imagine that you were going to be make a space station or something that's going to be this shape. And by the way, that would not be unreasonable, right? I don't know if how many sci-fi movies y'all have seen, right? But they make sort of this kind of shape space stations because then you get them rotating, and as they rotate, they create kind of a centrifugal force, sort of a pseudo-gravity. Right? So this is not an outrageous idea. Okay. So, how would you describe where you are on such a space station? Right? What would be the coordinate system that you would use there? You wouldn't use a rectangular system. That'd be really unnatural. This is highly non-rectangular. That wouldn't make any sense. And I'll tell you what I think would make a lot of sense. What would be the most easy? A coordinate system that's most tailored to what this shape really is would be that if I'm at a point here, right? Let's talk on the one hand about how much of an angle do I need to rotate from the this part of the XZ plane to get to it. Right? This would be this is what we would normally call theta, right? But I think that'd be a natural choice, right? Because this angle suggests a kind of a roundness, and our shape truly is round in that direction. So it is very natural. So this angle is what I'm going to call S. And then the other coordinate that I think would make sense is if you look at this point from which you rotate to get to our purple point that we're interested in, we can ask how far what you might want to call north is that, right? So what is this angle right there? That angle that I'm going to call T. And if you were to imagine an equator, as it were, going sort of around the outside of this donut, how far north of the equator? What is that angle? Measured from the center of the kind of the handle of the donut, not measured from way back here, but measured from the thing that our surface goes around, right? And our surface goes around, at least in this cross section, goes around that point, not this point. So again, this is we get to define whatever coordinate system we want, and just given the shape of this, I think these two angles are pretty reasonable. Does that make sense to everybody? You don't have to choose these. There are other options. I think you're going to have a tough time making a better choice than these two angles, but still, this is an arbitrary choice. Okay, and with these choices made, now we just have a geometry problem. All I need to do is to figure out how to write position on that point there as a function of these two angles, S and T. How would I find the coordinates of that point as a function of those two angles? So here's how that geometry goes down, and I'm going to be quick with this geometry because this is just geometry. A little bit of vector algebra and some geometry. But first, we'll talk about, let's see here. First, I'm trying to get all of this on the screen at the same time. Let's talk about this point, the point from which we're going to rotate, right? That point, which easier to see down here, if I kind of strip off all the other stuff. That point right there is pretty easily seen to be a sum of that vector, which is a constant. That's always a comma 0 comma 0. And then plus this vector. And now that vector, of course, is going to depend on your T angle that you have right there. You know what? I need to zoom in on this. Oh gosh, will it zoom? There we go. This purple vector, depending on that angle T, that purple vector is going to change. Right? Now, it's just a little bit of trig to think through how that purple vector depends on T, but nevertheless, that is some trig that you have to do, and what you will get is that purple vector depends on T by way of this formula. Make sure you can do this. Now, again, this is just trig, right? But it's you want to make sure that you're fully rehearsed and fully polished on being able to look at a scenario like this and think about the angle and think about the appropriate triangles and do the trig and get this right. Okay, good exercise. All right, so that being the case, adding those up to get our point P, that point being the sum of those is this. All right, the second part of this story, now keep in mind, the big idea is that point we just found is what I need to rotate to get the point that I want, I'm going to need to rotate by an angle S. Oh, wrong color. Need to rotate by this angle S. So, how do we do a rotation in 3 dimensions? Well, it's a linear algebra thing, isn't it? Right? Rotations are linear transformations. So I'm just going to write down the linear transformation that rotates around the z-axis by an angle S. That, again, classic linear algebra problem. And rotating by an angle S, like so. Again, angle S. You get this. So again, make sure that you're good to go with this kind of thing. Keeping in mind the big point is that a rotation is a linear transformation. Linear transformations are matrices. Matrices can be thought of in terms of their columns. And the key point, the columns are the images of the standard basis vectors. So you just need to take the standard basis vectors in this picture. Imagine what happens when you rotate them. Those rotated results are your columns here. So another exercise, another thing to make sure you think through, make sure that you understand all the ideas that go into identifying this rotation. And there you go. Okay, so, and now it's basically all over but the shouting. We already found that sort of projection point was this by geometry, and y'all are going to also confirm that the rotation is executed by that matrix, right? And so altogether, the point, arbitrary point on our surface, is what you get when you multiply the purple matrix times the orange vector, and that gives you this. Pretty hairy looking formula down here, I'll confess, right? But this parameterizes our torus. Okay. What do you think? Yes?
Can you please explain again how you got the rotation matrix?
Yeah, so this is a flashback to linear algebra. So the columns are the images of the standard basis vectors. So what you're going to want to do is go back to, so I have some discussion of this in the 1.6 lecture notes. And all of that, of course, is just kind of a rehash of old linear algebra facts. But so, yeah, you just have to take the standard basis vectors, geometrically rotate them, and then find the coordinates of those rotated results. Those become your columns. Yeah, right. Yeah. Okay, here's the last method I'm going to show you. Sometimes you can deform an existing parameterization. So starting with, here's a kind of a freebie, but this is a good example to see, though. Suppose you want to parameterize the unit sphere. No problem. The unit sphere is a graph, isn't it? Spherical, that is. It's a spherical graph. Rho is a function of phi and theta. A really easy function of phi and theta. It's a constant, right? But nevertheless, rho is a function of phi and theta. It's a graph. You use the graph parameterization, and you get this result. Now, make sure you understand the little connection I made there. Right? I'm applying our new idea of a graph parameterization for a surface. Get this result. Make sure you can do that. And you can write that down in coordinates. This is the exact same thing right here, just writing out explicitly that the first coordinate is x, and the second coordinate is y, third coordinate is z. So write it either way. It doesn't really matter. Okay. So now, harder question. Suppose I want to parameterize an ellipsoid like this. I don't know how to write the spherical equation for this. If you were to try to plug in your conversion formulas and kind of make that all work, you'd get something pretty nasty. And I guess technically you could solve for rho as a function of phi and theta, but I think it's going to be a nightmare. Right? It's going to be really weird. Okay. So what are you going to do? Well, there's a couple different ways you can think about this. In any case, though, notice that the difference between a sphere and an ellipsoid is just a matter of stretching. right? That's, if you have a sphere, stretching it out makes it an ellipsoid. So we just need to figure out how do I in the parameterization, how do I execute the stretching? You can tell from the equation right here, I'm going to need to stretch in the x direction by a factor of a, in the y direction by a factor of b, and in the z direction by a factor of c. How do I actually do that? And again, two different ways to think about it. If I want to stretch the x coordinate by a factor of a, here I did it. Notice I made the x coordinate literally a times bigger. That's all there is to it. If you want to stretch in the x direction, all your x coordinates are going to be a times bigger. That's what I just did by sticking in a factor of a right there. So that accounts for the stretch in the x direction. And likewise for the y and the z, and that gives you these other factors, b and c, right there. All right. Okay, so that's one way to think about it. Now, if you prefer, you might think to yourself, look, it's easier to see this as x getting replaced by x over a. We know from long ago that in an equation, if you replace all the x's with x over a, that is also going to perform the stretch. And so here I go. I'm going to take this equation here, I'm going to take that x, and I'm literally going to just replace it with x over a. So that's also pretty straightforward. Now it does seem to be a little contradictory that in one of these points of view I multiplied by a and in the other I divided by a. How do you know why to multiply or divide which one in which case? Seems a little contradictory. Remember, though, what we're talking about in this left equation over here is position, and so these are x, y, and z that we're writing down. And so really what we're doing is we're comparing this as an equation for x with this as an equation kind of involving x, but are these contradictory equations? Not at all. I just have the a divided over to the left side here as opposed to leaving it on the right side. These two equations I have circled in green are totally equivalent. So the distinction between multiply and divide is purely a cosmetic distinction in this case. In both cases, I've done exactly the same thing. Does everybody see how these two green equations are exactly the same? Morally, equivalent? Okay. All right. So either point of view you prefer is totally fine. Take your pick. So sometimes this works out really nicely. In this case, if when you're asked to parameterize an ellipsoid, you look at this and you think, well, I don't have any other good options, and then you remember that the ellipsoid, even though it is totally different surface from a sphere, it is closely related. It is a simple deformation of a sphere. So the idea is the fact that we already knew how to do this one, right, and the fact that there is an easy deformation that turns what I know how to parameterize into something that I want to parameterize, that's what makes this method possible. Okay. All right. Okay, moving along. Again, the book does have some examples. Again, they're all kind of backwards. They're interpreting existing parameterizations. They're not creating new parameterizations. And I think the stuff that I just showed, I honestly think what I just showed you is more useful, practically speaking, than what the book has. Okay, this next page is another page that we're going to largely skip. This develops some ideas and some details that are useful, but again, short on time and all of that. This is in the direction of proving a result. and it's a result that I'm just going to cite instead of walking y'all through the proof. Again, you're very welcome and encouraged to take a look at this development that we're just going to skip over here. But the big idea is what we're going to skip down to, and here we kind of go. I'm just going to jump in right here that if you have a surface, here I'm using a sphere, just as kind of an easy starter example, and if that surface is parametrized, and you have position as a function of parameters. In this case, I'm using phi and theta as parameters, reasonable choices. In that case, you can talk about, well, what happens when you move in the phi direction by a little bit? If you move in the phi direction by a little bit, well, then on the surface, you're going to move in the phi direction. Keep in mind the phi direction is the angle measured off of the upward part of the z-axis, right? So phi is that angle, and this is what happens on the sphere when you move in the z direction. And likewise, if you move in the theta direction, that's what happens on the surface of the sphere if you move in the theta direction. And so correspondingly then, we can talk about, with that noted, given a little piece of area over here in the phi theta plane, I could talk about the corresponding amount of area on the surface itself. Right? These two edge vectors representing little displacements will give me correspondingly some little edge vectors over here. That rectangle corresponds to this roughly approximately a parallelogram. Not exactly, right, but pretty close. So you might see this coming. We've done this kind of thing in advance. If you want to do business, say an integral, for example, on a undesirable domain. This is undesirable because it's dimensionally weird. It's a two-dimensional area that lives in a three-dimensional world. We can't. I don't know how to. Would it be a triple integral because it's three-dimensional, but there's no volume? What's going on here, right? When you have a bad domain where you want to do some business, you pull back through the parameterization. We're going to be rewriting stuff involving the sphere in terms of, by pulling back, stuff involving just phi and theta, happening in the phi theta plane. And related to that, we're going to need to know a stretching factor. We're going to need to know by what factor does the green area get stretched out to create this blue area. All right, so I hope that rings a lot of bells. This is ripping off the idea we did with change of variables. Also kind of ripping off the idea that we used for line integrals. Right? Pull back, you need a stretching factor. So we're going to compute that, and turns out there's a straight-up calculation for how to compute this blue area right there, and it's just a parallelogram in space, and we know how to compute areas of parallelograms in space. It's the magnitude of the cross product. You write that down, and having done that, we separate out the d phi and the d theta, and the result is the green area that I started with relates to the blue area that I'm interested in by multiplying by this factor right there. So that's our stretching factor. And again, I know we skipped over the details. How did I get that these are the edge vectors? That's on the previous page. You don't need to worry about that. Very analogous, though, to what we did with change of variables. So it's doesn't come entirely out of nowhere. I encourage you to take a look at that previous page. You don't have to. Punchline is we have our stretching factor. And so if you have something happening on the sphere and you want to rewrite that in terms of phi and theta, don't forget to insert your stretching factor, and everything's good. And here is sort of a formalization of that. Just as a label, just for notational convenience, I'm going to take this thing here, this cross product itself, not the magnitude, but the cross product itself. We're going to give that a name We're going to call it capital N. I'll come back in a second and talk about why. And so just for compact notational convenience, this stretching factor, magnitude of x phi cross x theta, I'm just going to rewrite that as the magnitude of capital N. This is very standard. Our textbook does it. Many other textbooks do the same. Little shorthand there. Okay, so there's your stretching factor. All right, now let's talk about this capital N thing. Let's see here, this thing right here. What can we say about capital N itself, that vector? Well, it is a cross product. You can visibly see it right there. It turns out that XS is one of these vectors, one of these edge vectors. XT is the other edge vector, well, it parallel to the other edge vector, and so this cross product of them is perpendicular to both. And now geometric appeal, if these two vectors are tangent to your surface, then the cross product is just going to be perpendicular to that surface. And that's why we call this a normal vector. Normal is a stand-in word for perpendicular in a lot of cases. Y'all have seen that before. So this is a normal vector to the surface. I like to call this the parametrized normal vector because you'll notice that the formula for this capital N comes straight out of your parametrization. You have to start with a parametrization x because that's what you're taking the various partials of, right? This comes from the parametrization. It is dependent on the parametrization. So I call this, again, the parametrized normal vector. Now, just heads up, the book instead calls this the standard normal vector. It's just a terminology, so I suppose that's fine. Here's why I'm not comfortable with that myself. Standard, to my ears, right, to just, the way that smacks in my head, standard makes it sound like it's unique. It's the standard, right? Like there's only one way to do this. And that's explicitly not true, right? I mean, there's lots of parameterizations, bunches of different ways to parameterize a surface. So standard seems like it's I don't know, I feel like that's overstating. I mean, I do get, of course, that it is unique to the parameterization. That's true, right? But I just feel like I don't know, I feel like it comes off a little misleading. Okay. So anyway, that's the terminology, and that allows us to answer a pretty hard question in a pretty easy way. If we wanted to compute the area of the unit sphere, and you may be thinking, yeah, we know how to do that from high school geometry, then I pose the question, how did high school geometry figure that out? Right? And there's different ways to come at this, but let's come at this using our new tool, and we can parameterize the unit sphere pretty easily. Old news. We've done that several times today. And now we just compute. First we take the partials. Then we take the cross product of those partials that we just computed. And the cross product, well, it's a bunch of, wrong color. The cross product, there's a fair amount of algebra that goes into that. You end up with this. And it's a good exercise, by the way. You want to make sure that, I know there's a lot of mechanics in this class, a lot of computations that have to be done. You've got to be really good at trig, right? To be able to go through all this stuff and keep this all straight and get down to this as an answer. Make sure you're that good at trig. It's going to be important. It's going to be necessary. And then lastly, we have to take the magnitude. And the way we take a magnitude, of course, old news, y'all know how to compute magnitudes. But there's, again, a fair amount of algebra that goes into this. You notice the ... The Pythagorean identity is going to come up several times as you go through and try to compute the magnitude of this big, super triggy kind of vector. And amazingly, the magnitude turns out to be just sine phi. And so when you do your pullback, and in doing the pullback, you have to insert your stretching factor. Your stretching factor is just sine phi. So the seemingly hard question of how would I add up all of the little pieces of area on the surface of the sphere to get the total area, well, you just integrate the stretching factor in the phi theta plane. Turns out to be a really easy integral. Easy and familiar answer. Okay, we're out of time. We're drawing the line right there. See y'all on Monday. Y'all have a great weekend. And don't forget office hours starts in 15 minutes.